Okay, still waiting. Okay, so this is lecture 02. Okay, again, the lecture, we are going to go from 7 p.m. and we'll go up to 10 p.m. Okay, so we're going to cover, we have our agenda for today is centric unsymmetry bending. In fact, this is a continuation from last week. Okay, and then we're going to look at eccentric symmetrical bending. This eccentric symmetrical bending, I think you guys have done in 2P before. Okay, I'm just going to refresh with you guys. Then we're going to go into eccentric unsymmetrical bending. Okay, and if time permit, today I also will cover sandwich material. Now, question for you guys: have you done sandwich material into P04? Sandwich material is a structure made of more than one material. Anyone? They all covered it in 2P. Anyone?
I think we covered it.
Okay, you did cover it.
Something that had more than one material.
Yeah. Okay. So I'll do symmetric sandwich material, and then it's under eccentric loading. Okay, sandwich material eccentric. Eccentric symmetrical bending. So when you guys were taught sandwich material is only centric, okay, so I like to have this amount of content in there. Okay, so let's look at, so last week, all right, so last week's lecture, okay, we look at an example like this, and also in our tutorial that we look at a structure like this. Okay, and now the thing is how to find the position of the neutral axis. Okay, how to identify the neutral axis. Okay, right, so we are going to look at again centric unsymmetrical bending. Okay, so the formula that we are going to use for this case, okay, with centric unsymmetrical bending, you have stress X is equal to my over Iyy multiplied by z minus by mz over izz multiplied by y. Okay, so if we were to draw our structure of analysis, I'm going to do something simple. It's going to be a rectangular structure. Okay, so that's our rectangular structure. And then we have our axis. So two of our axes. So over here, this is your y. And over here, your z. Okay. So what we're trying to do down here is we are trying to identify the position of the neutral axis. Okay, oh sorry, neutral axis. And a key thing to take note, okay, okay, centroid is not necessary equal to the neutral axis. Okay, there's always a perception that the centroid and the neutral axis are the same thing. No, okay, not the fact. Okay, so now important thing to remind you, okay, is this. Okay, I'm going to copy this. Okay, and I'm going to paste. Right. So a good thing to remember is this. Okay, so I'm going to rotate this by 45 degrees. So what you see down here, okay, so these are the axes. Okay. Okay. So important thing to take note is that the axis rotates with the object. Okay. The axis rotate with the object. No doubt, if now because we have rotated in this orientation now, a key thing to remember is this is still known as our vertical axis. So this is still our vertical, and then this is still our horizontal axis. Now, can anyone tell me why the axis rotate with the object? Okay, why this axis that I'm highlighting now always rotate with the object? Any idea? What are we trying to simplify down here? Anyone? Anyone? The question again, why do we rotate the axis with together with the object? Anyone, please? No? Yeah.
Because the forces applied are still on the same axis.
Not necessarily true, but you're partly right. Okay. Why? Okay, because the axis rotate with the object is to simplify. Okay, wrong spelling. Simplify the the determination of the second moment of area. Right? If you look at our structure now without rotation, okay, without rotation, so I'm referring to this diagram over here now, right? To find IYY, IZZ is easy, right? BD cube over 12, right? If we rotate, and if I want to find I about the horizontal axis and I about the vertical axis, it's more difficult. Yes or no? Okay, so I'll write down here it's more complex, not impossible. Okay, it's more complex. To determine the second moment of area about the, I will use the same color, okay, horizontal axis and vertical axis. Okay, so a key thing to remember, which I'm going to highlight down here, is the axis rotate with the object. Axis down here, I mean Y and Z axis. Okay, and I want you to remember that. That's very important. Okay, or not, it just make your calculation more complex. Right. So I'm going to call this now. So coming back to here, this is my equation 1. So we're going to identify the neutral axis, right? So we know that at the neutral axis, right, at the neutral axis, stress x is equal to 0, right? So if we're going to substitute or using equation 1, right? So we have this form, okay? So my over iyy z minus by mz over izzy. Okay, so again, to remind you, we are trying to locate the position of the neutral axis. Okay, now, so I'm going to draw two axes now. Okay, I'm going to draw two axes. Okay, I'm going to draw two axes. So this is my z, and this is my y. Okay, so this is my z. This is my y. Okay, and then for this to happen, we have two components of the moments. We got moments about the y-axis and moment about the z-axis, and this is our resulting moment. Okay, so I'm going to draw our resulting moment. Okay, so this is our resulting moment, and we're going to call it m. Now the resulting moment is rotated starting from the z-axis, right? And it's rotated by an angle over here, which I call theta. Okay, so you can see theta. So I'm going to highlight. So the theta is rotated, or is rotate, okay, from the z-axis. And for this case, with how I've drawn, okay, positive is clockwise. I highlight again, positive is clockwise. Okay, you have to remember this. Okay, so again, the moment vector is rotated from the z-axis. Okay, and clockwise is positive. Okay, so I want you to first construct this diagram first. Now, so from this equation over here, right, from our expression that we've done, right, we can rearrange the equation and we can get mz over izz y is equal to mz or my over iyy z. Okay, so we also can so I'm going to call this our equation number 2. Okay, equation number 2. Then I'm going to rearrange equation number 2 again. You have y over z, right? So you have my over iyy, right? And then you have mizz over mz. So this is our equation 3. Okay, and note this. Okay, if we're gonna let, okay, we're gonna let tangent theta is equal to my over mz, right? So where did this expression come from? Okay, so you can see over here from our vector diagram, right? We will know that m. So I'm going to sketch our my. Okay, so this is our my. All right, this is our my, and then we have our mz. Right, so this is our mz, So we know that my, okay, so from here, we know that my